so much to you all for taking this workshop. I know DSEM is something I'm particularly excited about, and I was so glad to see that so many of you also are excited about this and have data that might be appropriate for this type of model. So, all right, so we're going to talk about dynamic structural equation modeling today. So, just quick outline of what that will entail. So slides are going to be split up into about 5 sections. So today we're going to talk mostly about foundations. So dynamic structural equations is really kind of this hybrid of 3 different models. So today I'm going to talk about kind of the nature of intensive longitudinal data, how these 3 different methods that DSEM pulls from, and how they kind of blend together to form this, this new overarching framework that we call DSEM. So we're going to talk about today things like time series analysis. We'll get a little bit into multi-level models and a little bit into SEM or structural equation models. If you haven't encountered those before, that's not a requirement. I'll give you the relevant bits because it just borrows pieces from these different modeling frameworks. You don't have to be an expert in each of the 3 to combine them together. But I'll talk a little bit about the foundations of each one and some of those relevant ideas so that we all have the same solid foundation so that then we can springboard into some of the more advanced applications and advanced topics. So today we'll talk about the foundations. We'll end up somewhere probably in the middle of section 2 today, which is going to start to combine things together to form this overall DSEM model. We'll talk about some of the advantages of DSEM compared to some more traditional methods like mixed effects models or just strict multi-level models. And we'll talk about some practical issues about things like centering or unequal spacing between time points. So if you're doing cell phone data or something like that, where you're pinging people at random times, there's some design and statistical issues that come into that. So we'll make sure we talk about some of those details. As we move into the second day of the seminar, we're going to talk about building up these models with covariates that are either time varying, which means you're collecting them at each individual time point as well. We'll also talk about time invariant covariates to say things that you collect once at baseline or are trait-like characteristics of people. And then about the middle of day 2, things will really start to get nuts. So we'll talk about expanding these things with things called heterogeneous variance models, things that are hard to do in other frameworks. We'll talk about things, residual DSEM or RDSEM for systematic trends. And then we'll get into models that have multiple outcomes at the same time, or that you have small groups, so dyads or 2 or 3 people who you're tracking simultaneously, and you want to see how they kind of they co-regulate or kind of change together. Then we'll talk about some things that are particularly relevant to behavioral researchers, things like mediation models, things like measurement, that when you kind of look at the intensive longitudinal data in biostatistics or maybe a more health application where you might not see these covered as much, but DSEM is real strong at being able to incorporate these more psychology or behavioral aspects. And then time permitting, hopefully we'll have time for one out of 2 of these topics, but we can talk about some probit models when you have binary or ordinal outcomes. So if you're asking people Likert scales or yes/no questions at multiple times, there's slight different variations of these models that you can use in those contexts. We also have some slides on missing data, particularly MNAR missing data, because DSEM is used for sensitive topics, substance use, mental health, sexual behavior, things like that, where sometimes people are missing for an informative reason, and there's some ways we can incorporate models that deal with some of that MNAR. So these last 2 topics we might not be able to get to in full detail, but I have full detail slides on those topics, even if we don't get to them, that you have for your own edification if you have these issues in your own data. All right, so that's where we're going. So let's go there now. So jump right in. So section 1, some of the foundational topics, building blocks of DSEM. Again, I said DSEM is the combination of 3 things: time series analysis, multi-level models, and structural equation models. So just talk about the bits and pieces of this that are useful, and also how they combine together to give us this new framework. So Before we jump directly in, I just wanted to talk about different types of longitudinal data just for a couple slides. Um, Especially because when I was in grad school, not so long ago, maybe longer than I hope, but longitudinal data meant something a little different than it does now. So when I was in grad school, longitudinal data meant growth modeling, and that was kind of the only thing that it meant. Now, starting around 2015-ish, we start to get different types of longitudinal data. So I just wanted to talk just a couple slides about what types of longitudinal data that DSEM is appropriate for, or tends to be a possible model you might want to consider. So longitudinal data, basic broad definition, is just saying that I have multiple observations per person, or that I'm repeatedly measuring the same individuals. So there's different ways this can look. And so there's different models that kind of match the different types of designs where you might have longitudinal data. So often in graduate programs, there's a class called longitudinal data analysis, but sometimes it might focus on one type or a different type. And in this DSEM seminar, we're going to focus specifically on one type. So there's obviously much finer gradations, but I'm just going to split it into two very broad categories where I'm going to say panel data is one type of longitudinal data, and I'm going to say intensive longitudinal is another. So the characteristics between these two are kind of in the design and how many time points that you're going to collect from each person. So in panel data, this is the more traditional data pre-smartphone that you often see, where you're following people, you're measuring them repeatedly, but only a couple times over very spaced out time windows. So you might have somewhere between about, I'll say, 2 and 10 observations per person. But there's going to be a fairly long interval between each repeated measure. So you might have, take one measure, wait a couple weeks, couple months, measure the person again, wait another couple weeks, another couple months, measure them again. And the goal of this type of design is usually for some sort of developmental process, that you're waiting for something to systematically change over some interval, and you want to be able to observe that developmental change as time goes forward. And so this is usually when people talk about growth modeling, they're talking about this first type of data where you have a few repeated measures and a long time window. Starting roughly 10-ish years ago, we've started to move more towards this bottom type of longitudinal data, which I'm going to generally call intensive longitudinal data, where the research design is more interested in densely collected observations over a very short time interval. So usually we're talking 20 or more observations per person. You can sometimes have less. That's not an issue. So if you're doing a 2-week daily diary and you have only 14 repeated measures, you can still be in this bottom category. But there's some studies that'll have hundreds or thousands of observations. Usually the spacing is very, very narrow. So we're talking seconds, minutes, hours, maybe every day or two. But I'm not waiting weeks, months, years to collect data. And that's usually because the interest is in momentary variation. I'm not trying to follow some developmental process like learning to read or something that's growing. I'm caring about where people are moving from moment to moment, which I'm going to talk a little bit more in the next couple slides. So, but this is the kind of at least in the longitudinal statistical literature, if you do a very rough split of types of longitudinal data, this is kind of the one line you can draw. Are you trying to model growth, or are you trying to model variability from time point to time point? And so just to put this in graphical terms, because it's a little bit easier than just putting a slide full of words. So developmental process, usually it's some growth curve. So you have this outcome that's changing over the course of time. And your statistical model is mostly based around trying to capture that functional form of growth. So are the scores growing linearly as time goes forward? Are they curving? Are they asymptoting out? And you're trying to see if this is, what that functional form is, and then trying to capture individual differences in the growth rate. And if there are individual differences, some people are growing faster or slower than others or steeper. trying to identify covariates that identify or predict those individual differences. What makes person 1 grow faster than person 2? What makes person 3 start higher than person 4? Questions related to that. And again, as I mentioned on the previous slide, very spaced out measurements here. Growth models tend to be appropriate. So if you've taken a longitudinal data analysis course before, this is often one of the focuses to say functional form, trying to fit lines through things, getting individual differences, and then mostly focused on time invariant covariates. So what are characteristics of different people that result in them having different growth trajectories? This is not the kind of data we're going to focus on here, but this is one that if you Google longitudinal data analysis or open a longitudinal data analysis textbook, you will see a lot of these types of models. The context that we're going to focus on is more something, at least for the first half of the slides here, is something called a stable process, which there's not systematic growth. There can be, but there's not necessarily, or the main interest is not systematic growth from the first time point to the last time point. Instead, the process, it might be stable or it might have some kind of recurring trend. So here I have this dashed line going through this dashed gray line, if you kind of look a little closely. And I see that if I draw the mean line or some mean trajectory through my data points here, it's basically flat. That there's not a systematic change in this outcome as I go from the first time point to the last time point. But that doesn't mean that there's not necessarily something interesting going on here. I see that this person is peaking and spiking as time goes forward. Sometimes the outcome is very high, sometimes the outcome is very low. And when you have data that look like this, that are collected intensively, a common interest is about the momentary fluctuation. And saying, if I look at the very left of this plot, I see this peak right after the measurement window starts and say, I wonder what happened at that time point that caused the outcome to spike up like that. So if this is something like, desire to smoke, for instance, was this person anxious at time point? Looks like time point 3. Did something happen? I'm more interested in the momentary information around that time point rather than the very zoomed out information of just generally what is the shape of the line. And so models for these type of data generally focus on momentary characteristics. I'm talking about carryover or spillover effects from one time to the other. So again, if this might be something like desire to smoke, if I had a strong desire at one time point, does that carry over to the next time point? Do I revert to my baseline? Once I get stuck needing a cigarette, do I basically stay in that state until I satisfy that, possibly by smoking? The interest is more the ebbs and flows over time. I'm not trying to fit one line that best kind of just captures the general growth trajectory. I really care about the individual time points and the variance from time point to time point. And so that's one of the main differences as we start to get into these more intensive longitudinal data, is that our focus shifts from growth trajectories and linear versus nonlinear curves, and we more so focus on within-person variability. That if you zoom out far enough, my line might look flat, but if you start to zoom in a little bit, you start to see peaks and valleys or ebbs and flows in the data. And those are interesting because of that moment-to-moment variance and the dynamics as that system kind of moves forward. And so intensive longitudinal data are great for looking at these types of questions. They're not necessarily interested in development, because if you're measuring someone every couple hours, every couple minutes, there might not be enough time to see some systematic development unfold. But these data can still be great for getting at the richness of daily life, particularly as it's occurring. And so this is kind of the main split. Am I trying to capture some broad developmental process, or am I trying to zoom in and capture the moment-to-moment system here? All right. So one type of intensive longitudinal data, which I'm going to in this third bullet point here, or one feature that comes up commonly in intensive longitudinal data is this idea of mean reversion, which is that there might be temporary increases, temporary decreases as time goes forward. But basically, if I fit an overall line through my data, it would be horizontal or close to horizontal. And this idea comes up a lot in intensive longitudinal data, usually referred to as stationarity. Um, and so this is another distinction within these types of intensive longitudinal models. Is it the model for stationary systems, or is it for non-stationarity? So in these notes, we're going to talk at the beginning about stationarity models that assume that. That tends to be the general case, but we'll move into some models that don't require this as we go forward. I'm not going to read this table to you, but this is just up here for now. So again, this is just basic distinctions between the more traditional developmental process or growth model type data and the more stable process or intensive longitudinal data. Um, so this is here for your own edification if you want to look at that in some more detail. But again, main difference is spacing between measurements. Am I looking for something that's growing over time and I need time for that thing to unfold? Or am I looking at very closely spaced repeated measures, and I'm more interested in the peaks and valleys rather than pure development? As was alluded to in some of the questions in the chat so far, not all intensive longitudinal data are strictly stable and have this mean reverting process. It is possible to have both together at the same time. So this is particularly the case if you're doing some sort of intensive longitudinal interventions. You might have people who are systematically decreasing over time. So if you're trying to change behavior or increase or decrease the outcome, you might have elements of both of these types of modeling frameworks, which again, we'll talk about. I believe it's that second, either section 2 or section 3 of the notes. We'll have an extended set of slides talking about these situations because they are so common. And we'll get into things like detrending and residual DSEM, which is a spin-off that deals with this type of situation. This is more of a systematic trend where the line is generally decreasing. You can also have cyclical trends or seasonality in your data, which if you work with substance use, you might see this like weekend effects. If you study something like alcohol consumption or alcohol use, tends to be higher, Friday, Saturday, Sunday, maybe not so much during the week. So you can have non-stationarity due to cycles. Which we'll also talk about in that set of that second or third section when we talk about the non-stationary case and how to incorporate some of that into these dynamic structural equation models. So, all right. So to bring it all together before we jump right into DSEM particularly. So in this course, we're only going to talk about DSEM. We're only going to talk about intensive longitudinal data. The first half of the slides are going to focus on stationary processes, that mean reverting system, where basically if I drew a line through things, it would be horizontal, and people are ebbing and flowing, but they're not systematically changing. That's the slightly easier case to deal with, so we'll start there. As we build up, we'll get into some of those more complicated aspects that may come up depending on what area you're studying. So that includes systematic trends, cycles, things like that. Very broadly, dynamic structural equation models combine 3 different things together. So multi-level models, structural equation models, and time series models. Together, these things are going to help us account for different nuances and different features of intensive longitudinal data. And as we'll see towards the middle of day 2, end of start of day 3, the benefit of combining these different models together is it really helps us expand the types of questions we can ask. So if you're familiar with some of the more traditional models for intensive longitudinal data, the models we talk about today, you might say, I can already do that. But the models we're going to talk about day 2, day 3, it's a little more difficult to fit into a traditional model, like perhaps a mixed effects model or something like that. So things like mediation, measurement, multivariate theories of multiple people or multiple variables kind of co-affecting each other or have co-associations, DSEM is going to be really well aligned for those types of ideas. So, all right. Any general questions just on the type of data that we're focusing on here, or the types of this general idea of developmental processes versus more of a stable process or stationary process? No, that's okay so far. All right, then we'll jump into some of the foundations. So I know backgrounds are varied, so I know some of you might be very familiar with this. Some of this might be your first time seeing it, but I want to make sure we're all on the same page before we start jumping into more of the complex models. So building foundations, borrowing ideas from these different existing frameworks to create a new framework that combines things together. So first we're going to start key ideas from time series analysis. This is one of the core components of dynamic structural equation models. And so time series analysis is a way to kind of deal with this repeated measure structure, particularly when your focus is not in some sort of developmental process. So a lot of time series models, a lot of the time series literature comes from n=1 cases, typically in things like finance, meteorology, or economics. And so often when people talk about time series analysis, they're talking about the multiple repeated measures on a single entity. So in this literature, you'll see like the price of a single stock if you're in finance. How is Apple's share price kind of moving over time? How is it ebbing and flowing? What are some of the dynamics about where it's moving? And people use some of these models to try to predict, where prices are going next. You'll see this in weather, so temperatures, aspects of weather measured repeatedly over one unit. So that's like, a city or a particular zip code, for instance. This is the more traditional application of time series analysis. As we'll talk about in a couple slides, behavioral data usually deviate from the traditional time series case because most of our studies have more than one unit that we're studying. So the sample size tends to be greater than one, which can complicate things a little bit, which is why we're going to borrow ideas from multi-level models to kind of combine with time series analysis, which we'll talk about when we get there in just a minute. Before I talk about how we deal with the n=1 case that I imagine most of us are dealing with when we have these intensive longitudinal data, I'm just going to pick out a couple of the ideas from the n=1 literature that are going to be useful to us as we start to build these models up a little more. So we saw this picture previously on a couple slides ago. So this is an outcome from a study on urge to smoke for someone who has recently quit. So their urges to smoke or use nicotine. So this is going up and down as time goes forward. They're followed 50 times, about 3 to 4 times a day. So it's a couple weeks. I'm not looking for very broad developmental changes. Instead, I'm looking at the ebbs and flows over time. The dashed line in this plot is the overall trend, which is basically flat in these data. It's mostly mean reverting. It's mostly stationary. Again, those are synonyms to mean roughly the same thing. But if I look at any single time point, the mean isn't always a great description. So I'm really interested in the moment-to-moment change. Why is the urge to smoke so high at some time points? Why is it so low at other time points? And about that with in-person variability as time goes forward. So again, this is an n=1 case. Right now, we're just imagining I have a single subject design. I have one person. But again, this is not the typical case, and we're going to add some features to incorporate data with more than one person in just a couple slides. So when you're setting the data up for something like this, particularly if you're going to work in the M+ software that is the focus of this course, you're going to want to have data in the long format. And so just a quick description of this. So when you have longitudinal data, you can put it in 2 separate formats. So there's wide versus long. So wide format means that every time point is its own column. The long format means that every time point is its own row. And so that's for all of the data that we're going to work with in this seminar, we're going to want data in this long format where every row, I see I have a time variable here. My outcome is this leftmost column, urge to smoke. Every successive row that we have here, this is a new time points value. And then I have a variable on the far right that is an index that indicates from which time point that data originated. So just if you're at the very beginning of embarking on an analysis and want to know what the format should look like, long format data for most DSEM applications. So in intensive longitudinal data, where you're going to measure people many times, often in close proximity, something that is often a concern is autocorrelation, which basically, so I have the idea of autocorrelation is that I have this mean reverting system, but if I collect data from people at very close intervals, there might not have been enough time that has elapsed for people to return back to their baseline. So if I follow you at 12 p.m. and you say, yeah, I really have a strong urge to smoke a cigarette right now, and I ask you again at 12:02, I say, do you still want to smoke? And you're probably going to give me a very similar answer, that there hasn't been enough time that's gone by for you to kind of come back down to your mean level. The closer in time that you collect data, the more likely it is that successive time points are going to be highly related to each other. You usually don't see this in that more traditional panel data, because if I ask you your math scores when you're 6 and your math scores when you're 9, you might not have this very strong autocorrelation. But if I ask you an hour apart or 2 hours apart, there might be some carryover or some inertia from your previous time point to the next time point. So this is something that is often not necessarily unique, but something that is more of a concern or more frequently included in models for intensive longitudinal data versus more traditional growth data. And so usually in these models, we'll use some sort of autoregressive structure where the current time point in our model is predicted by a previous time, by one or more previous time points. So if I want to know about your urge to smoke this afternoon, a strong predictor of that might be your urge to smoke this morning. Might not be perfectly related, but it's probably a good place to start, because those things are probably going to be highly related, especially in designs where you're taking measurements from people very close together. This is going to be a feature of most DSEM models. There's going to be some degree of autocorrelation or carryover from one time point to another. If you look at models for intensive longitudinal data broadly, they don't all use autoregression. Most DSEM models do. If a model doesn't have autocorrelation or carryover, it may not be a DSEM at all. It might be something like a multi-level structural equation model. So this tends to be a feature of dynamic structural equation models, is that the data are collected closely enough that there is some carryover or autocorrelation that should be modeled. Okay, so I've used the word carryover. That's what I'm going to use predominantly in the slides, but this goes by lots of names depending on what field you're in. You might have seen this called inertia or momentum. All of those are essentially synonyms to mean the same thing, which is that there is some relation from the last time point to the next time point, meaning that people don't go back to baseline between time points when they kind of get into these trends of when they are if you're above average at one time point, you're likely to stay above average at the next time point. All right. So what this looks like if you're thinking of setting this up in a statistical model is usually it takes the form of a lagged predictor. So if I have this regression model here, if I have urge to smoke in this example as my outcome, so urge to smoke with a little t here, subscript, so that's urge to smoke at time t, where this subscript t is just an index for time. So it just goes from 1 to however many time points I have. I have some intercept here alpha, just like a regular regression model. And then I'm going to have, you can use beta as your regression coefficient, but in this literature, phi is more common. So I'll have phi as this carryover or autoregressive effect. And my predictor here, the subscripts start to matter. I see urge with a t-1. So that's the previous time points value of the outcome. It's not a separate variable. It's just, I'm just lagging this predictor a little bit to say my outcome is the current value of urge to smoke. My predictor is the previous value of that outcome. You might note, what about at time 1, what happens? The lagged predictor will be missing at time 1. And if you're in this literature, this is called the initial condition problem. And we'll see this pop up in some later slides. And DSEM has some ways to try to address this, particularly something called Nichols bias, which we'll see later on in the notes. So essentially, the most basic form of this AR1 model is just that I'm predicting current values of my outcome from previous versions of the same outcome. We can add other predictors in here as well, but this is the autoregressive form or autoregression that we'll see carry through most of the models that we're going to talk about. So this is the main component of time series analysis that DSEM is going to borrow or rely on as it starts to build models up. So similar to other models, this autoregressive model is going to assume a normally distributed error term. So that's the last term off on the right side. Usually autoregressive models are referred to with a number at the end. This number just refers to how many lags you're going to use. So an AR1 model just uses the previous time point. AR2 models would use 2 previous time points, and you can kind of see the pattern from there. One note in a time series model is that the alpha term here is not the mean. It's not the line that people are reverting around. That's again because intercepts are conditional on all the predictors that are included in the model. So it's an intercept, but it's not the mean of the time series. And so if you want to calculate the mean of the time series, if you wanted to talk about the value that people are reverting around, there's this little formula here where you have to take the intercept and divide it by 1 minus the autocorrelation. Okay. Oh, sorry, there's a question in the chat that I didn't see. Is the autoregressive effect confounded with the number? So it depends. So does the question is, does the autocorrelation depend on the number of observations per person? It can a little bit. It also depends on the, more so on the spacing between the time points. If you have very dense data that are very close together, it'll probably be very high. If you have if data are more spaced out, it will trend towards 0, possibly even negative in some cases. I don't know if you just have a few repeated measures, if that will systematically affect things. You might get more sampling variability in that case. But I don't know for sure if that would make it necessarily smaller. Usually it's a function of the spacing of the data, at least if I'm understanding the question correctly. All right, so just in terms of fitting the model, and so we'll just get just to see what some output looks like. So nearly any software that can fit regression is capable of fitting an autoregressive model in this n=1 case. You either create the lag yourself or the software that you're using has some built-in function. I'll just briefly go through what this looks like in M+, because most of the advanced models we're going to fit are M+ specific, at least right now, as open source software is trying to catch up in this DSEM framework. And so if you're in M+, you don't have to create any new variables on your own. So M+ has this nice function, this lagged function. You can just put the variable that you want to create a lagged predictor for, followed by parentheses to say how many lags do you want to create. So here, the outcome variable that I have of interest is urge to smoke, which in the data set is just called urge. I'm going to put a 1 in parentheses there to say, give me the first lag or the previous time point of that variable. And M+ will automatically create that and allow me to use that in my code. This middle part of the code here, I don't have it highlighted, but DSEM models and M+ are only supported with Bayesian estimators. Talk a little bit about that, but it doesn't affect this is more done for computational reasons rather than philosophical reasons. Won't spend a ton. You don't have to be a hardcore Bayesian to understand and interpret the results of this model. So in M+, setting up an autoregressive model is fairly straightforward. So if you just put the outcome variable on as the keyword in M+, and then for regression, and then if you, the keyword in M+ for a lagged predictor that's been defined in a lagged statement above is just an ampersand. So urge on urge ampersand 1 just says take the urge variable and predict it from the previous value. In M+, there's just two other parts of the code that we'll see a lot as we go through these. An outcome variable by itself with a colon after it is a variance. So this is just saying estimate the second part of this model statement just says give me the residual variance. If I see the variable name in brackets by itself, that's just the intercept. So this model basically says I'm going to estimate three things: autoregressive effect of the previous time point on the current time point. I want the residual variance, and then I want the intercept. So mentioned this previously. So Bayes estimator, again, for computational reasons rather than philosophical reasons. These models often have a lot of latent variables. When we start to build up, they have a lot of random effects. At that point, maximum likelihood sometimes breaks down, and Bayes methods can be a little more efficient or expedient. So if you're working with M+ and you're trying to fit dynamic structural equation models, it won't let you do it with maximum likelihood. Bayes is going to be the default option here. All right, so if you want to think about the model graphically with a path diagram and try to put the code onto the different paths that are going to show up in this model. So my outcome here is on the right. That's urge to smoke at time t. I have the lagged version on the left, so that's urge to smoke at the previous time point. That's the lagged relationship there. I have some intercept, which in path diagrams are represented by a triangle. And then I have an error term, and its variance is just represented by the outcome variable by itself. So setup of a basic autoregressive one model for one person. Again, this is a time series model, the very basic version. We go through the output real quick just to get an idea of what comes out of these models if you haven't seen them before, or if it's been a while. First row here, this is the autoregressive effect. It's positive and it's non-null. So in the output in M+, M+ will give you the output almost in a frequentist form. It has this line for significance here at the far right. If you're a philosophical Bayesian, you might object to this and say, I don't think significance is a term that applies to Bayesian analyses. I totally see that point. I think the M+ output is just trying to make it accessible to people who are used to frequentist analyses. So the significance flag comes from testing the credible interval here. So it's just a flag for if 0 is within the credible interval or not. If 0 is not in the credible interval, you'll get a star there. If 0 is in the interval, then that flag will not appear. So autoregressive effect here is about 0.3. So there's some positive carryover from one time point to the next. So if somebody has a higher urge to smoke at the previous time point, they don't reset completely to baseline at the next time point. That's what you would see if the carryover effect were 0. In this case, the value is more likely to stay high if the previous value was also high. So I have some carryover going on. If I want to calculate the mean of this time series, so what is the horizontal line around which these data are kind of bouncing around, we saw that little formula on a previous slide. And if we take the intercept from the second row and divide it by 1 minus the autoregressive effect, it's about -0.08. So that's the typical value on this outcome. So I believe it ranges from -10 to +10. This person's basically right in the middle there, slightly below 0, but that's where their values are kind of bouncing around. So that's the horizontal line. So regarding the interpretation of the autoregressive effect, provided that the assumptions are met, which we'll talk about in just a couple slides, the carryover is going to be between -1 and +1. So the interpretation becomes fairly similar to like a correlation coefficient. So if it's 0, basically means there's no association. As it starts to get towards the plus or -1, absolute value of 1, basically means that the auto regression or auto correlation is getting much, much stronger, where the sign just indicates the magnitude. Is it positive? Almost always positive in these data. Rarely, it is possible to get negative carryover effects, which means that if you're high at one time point, you're more likely to be low at the next time point. But in most intensive longitudinal data, you see positive carryover effects. So questions that came up in the chat, what's the scale of the urge to smoke variable? It's -10 to +10, I believe. So it's about 0 is about the midpoint. Is the predictor raw in this case? Yes, the predictor right now is raw. We're going to talk about centering soon, but for right now, we're just in the most basic form where the predictor, I'm using the raw version of the predictor, just taking whatever the previous time point was. All right. Bottom row here is just the variance. I don't have any predictors yet in my model, so this is going to be pretty large. So the residual variance is about 8. Again, this is the scale of this variable is -10 to 10. So a variance of 8 indicates that there's a lot of within-person variance here. So even though the mean of the time series is pretty close to the middle of the scale, each individual time point is not necessarily right at 0. There's a lot of ebbs and flows. There's a lot of high values. There's a lot of low values. So if I kind of use the take 2 standard deviations, so if I take the square root of 8 and kind of add 2 or subtract 2 to try to get maybe like a 95% interval around the outcome, seeing that this person is bouncing around between about -6 and +6, which is consuming most of the scale here. Sometimes they're kind of blowing up to a positive value. Sometimes they're coming down to a negative value. So high variance here with positive carryover. So this is the basic idea of the autoregressive model. So if you've seen this before, I know this might sound familiar. If you haven't seen it, this is what's going to be a focus of models going forward. This model is mostly just useful for quantifying, without covariates yet, mostly useful just for quantifying the variability and kind of what the data kind of look like. So we saw that this person is kind of right around 0 on average, but there's a lot of variability. I'm usually not happy just to know that a lot of variability exists. I usually want to go in and try to explain that variance as well, to say, why is this person's urge to smoke varying so much? Why does it have high peaks? Why does it have low values? Can I associate that with something else to help me try to predict why this person might be bouncing all over the place in terms of their behavior? So in these models, we can add some time-varying covariates to better explain aspects of why this outcome is moving. So time-varying covariates are variables that are also collected at every time point. So in a growth model context, it's often the characteristics are collected just once, maybe like a baseline. In intensive longitudinal data, it's common to have covariates that are similarly collected at every time point, just like the outcome. So that's true in these data. So the data also contain scores that are depression symptoms or negative affect, depending on how you want to phrase it. But there's 50 time points in these data. So I have 50 times for urge to smoke. I also have 50 measures of this depression variable as well. And I can use that as a covariate to say, does the person's time series on urge to smoke, does that increase when depression increases? Is there any relationship between that? Does that help me predict where the scores are moving, if scores are going up or if scores are going down? So we can expand the model that we saw on the previous slide, start to add some covariates in. Say, now I have urge to smoke as my outcome on the left. I have that intercept alpha, and then I have the carryover or autoregressive effect phi here being multiplied by the previous time points urge to smoke. I now have this new predictor here. So this is a depression score at time t. So it has a t subscript because it's measured uniquely at each time point, just like the outcome. And so this is going to be a z-scored measure of depression. So it's going to have a mean of 0, standard deviation of 1. Add that into the model to try to help me predict the peaks and the valleys in that urge to smoke variable. If you're interested in calculating the mean of the time series, that changes slightly when you start to include time-varying covariates. So we need an extra term here on the right to try, if we're going to try to capture what the overall average is of the time series. So if just to kind of build up the software code a little bit, just in this AR1 example, only extra thing we're going to add here is highlighted. So if you want to add a time varying covariate, that's just the outcome followed by on, and then whatever our time varying covariate is. So in this case, DEP stands for depression. So we'd add that into the code if we're trying to fit this in M+. And if you want to think about it as a path diagram, just adding this term on the bottom at the right here, saying that there's some depression value that's a time varying covariate. It predicts urge to smoke at time t. And then to finish up this foundational example, just to say again, first line here is the carryover effect. Now starts to increase a little bit, saying 0.35 is a carryover. So again, it's positive and it has a little significance flag. So say it's non-null. Carryover seems like it's different from 0. What I see at the bottom here is that the residual variance has gone down notably. It was 8 before, now it's down closer to 1. So again, the residual variance is going to be unexplained sources of variance. Once I add this depression variable in, it's no longer unexplained. I can now attribute that variance to a time varying covariate. And I can start to say that the reason that scores are going up or down is because of people's affect, that when they're feeling blue, if they're feeling more depressed, that's going to indicate what direction that time series is going to go. And so can also see this if we look at the effect of this depression variable. It's about 2, so a 1 standard deviation increase in depression is associated with about a 2-point increase in urge to smoke. Again, urge to smoke is on that 0 to 10 scale, and we see the little significance flag over here indicates that this is plausibly non-null because 0 is not in those credible intervals there. There were 2 questions in the chat. So would you always want to convert a covariate to a z-score? Not necessarily. So that's how these data are set up. In an n=1 model, that z-scoring can make some sense if that is a relevant metric. When you get into n greater than 1, sometimes standardizing can make interpretation a little more difficult. Because if you have multiple people, you have to pick which variance you want to standardize by. So do you want to standardize across the variance just of that person's data? Do you want to pool the variance across all people? So generally, these data happen to have a z-scored metric, but in general, z-scoring is not always is not something that's commonly done, especially in these data where your predictors usually have an interpretable metric. Second question was, is standardized before, can M+ standardize variables? M+ can center variables. I don't know if it can standardize. You might have to do it manually. So there's a define option in M+. If you know the mean and the variance of your variable, you can manually standardize it, but I don't know if there's a quick standardized equal option in M+. Last question was, can this be done in R, Stata, Python? Yes, for these basic models, it can. For the when we start to build this up into a more complicated model with incorporating elements of different things like multi-level models, SEM, there's not an R package that I'm aware of that is nearly as general as M+. I don't think Stata can do most of the models we're going to talk about. I don't think Python can either. The DSEM that combines things as when we get to the combining the three pieces together, that was first paper on that is about 2018. The software has M+ is kind of the pioneer in that software, and other softwares have not quite caught up yet. So at least if you're doing some of the more advanced DSEM models that we're going to get to towards the end of today, towards second and third day of class, that's going to be very difficult to do it in software outside of M+, unless you are very proficient with Stan and want to code it as a pure Bayesian model. All right. So just last thing, just graphically, if you want to try to get at this type of the relation between these two things, this is called a gradient plot. I have the time series here, and the color of the dots is represents what the value of the time varying covariate, that depression score, what that was at each of the time points. So see, the darker the blue, the more stronger the depression score was at that time point. And you can see that effect was very strong, and you can see mostly the blue dots are all when urge to smoke was high. The red dots was roughly when it was low. And this is kind of supporting that, what we kind of interpreted that output in the previous slide, saying when those depression scores momentarily increase, the outcome urge to smoke momentarily increases as well. I see that there's kind of a strong relation between these things, that as one goes up, the other kind of goes up with it. That if I want to know what causes or what is related to this person's urge to smoke, it seems like how their affect, particularly their negative affect, is going to be a strong predictor of that. And if you want to make this slide in R or SAS, that's just on these next two slides. I won't read that code, but it's just there for you if you are interested. So last piece of autoregressive models that we're going to take when we start to build DSEM models is this idea of lagged versus contemporaneous relationships. So this is an idea that comes up particularly with time-varying covariates. And that is whether the covariate needs some time for the effect to unfold, or whether the effect of the time-varying covariate is essentially immediate or instantaneous. And so in the model that I just showed, I modeled depression as a contemporaneous effect, that I had depression at the same time point, predicting urge to smoke also at the same time point. So if I go back to that path diagram that I showed a few slides ago, I had urge at time t being predicted by depression at time t. Both of those things have t subscripts. That's what makes it contemporaneous. That's one definition when people talk about these models, talk about how the model was built. That means the time-varying covariate is included in a way that the effect is from the same time point. The predictor is at the same time point as the outcome. We can have lagged time-varying covariates. So if we think that some time mechanism is required to unfold, I can have depression at time t-1 also predict the outcome at time t. So I don't necessarily have to have my predictor and my outcome at equal time points. I can have them be lagged if I think that is, if I believe that is the mechanism by which that variable affects the outcome. The decision between whether to include a covariate as lagged or contemporaneous is mostly driven by kind kind of the hypothesis or the research question, how you think those two variables relate. In my context here, urge to smoke, I might say that contemporaneous might make sense, where I might start my negative affect might start to increase, and that as soon as that happens, I might reflexively reach for a cigarette to try to calm that down. So that might be an argument for a contemporaneous effect. You could also argue for a lagged effect to say, my negative affect starts to creep up, and that'll start to influence my urge to smoke a few hours later at the next time point. That it's not instantaneous, but the mechanism or the dynamics of these two variables, there needs to be some time that elapses between that effect. So in that case, I would include might include that time varying covariate in a lagged form rather than as a contemporaneous form. You can also include both of the covariate in lagged and contemporaneous forms at the same time. So, and you could estimate different effects of that. So I could say, if I have my depression or negative affect as high right now, that might affect smoking in one way, versus my previous time points, depression symptoms might affect my urge to smoke in a different way. So if you see these models sometimes fit with adolescents because they are on their phones frequently. And so you see those different forms of the predictors, sometimes like in the sexting literature, you'll see that, sexting effects affect differently if it's lagged or contemporaneous. That contemporaneous effects might be a positive coefficient, that it's fun and it's exciting in the moment. But the lagged time point, that as more time elapses, people start to have some negative feelings or might regret engaging in that type of activity. So same type of predictor might affect the outcome differently depending on the time that has elapsed. So just something to think about with time varying covariates as we're specifying models, and we'll see this come up as we start to build these up a little bit. Benefit of lagging the time varying covariate is something called temporal precedence, which helps if you're interested in causality. If you lag the covariate, you have a little bit, you have this ability to say, to establish causality a little easier, because if the covariate happens first in time and then the outcome happens second, you have this there's this separation in time, versus when you model things contemporaneously, you might have bidirectionality threats to say, well, I really don't know if X causes Y causes X. But mostly interested in what your research questions are and what the mechanism that you hypothesize might be. All right. Questions on lagged versus contemporaneous or time varying covariate effects? Is the effect of the predictor partial for the effect of the lagged criterion? Yes, it would be. Similar to another regression, it would be holding the other predictors in the model constant. All right. Last slide here, or last couple slides just on this before we start to expand and start to combine different modeling ideas together to form a DSEM. So a couple of autoregressive assumptions. So if we're assuming stationarity, these are kind of the components of stationarity. So first one is that the expected value of the outcome is constant at any of the time points that you have. So this is basically saying that the mean trend line is going to be horizontal, that there's no systematic trend or no cyclical trends in the data if stationarity is upheld. The simple model that we saw on the previous slide, where we're just including lagged predictors, this is going to embed this stationarity assumption, that the interpretation that we saw will hold if this is true, that if there is no systematic change and that line is horizontal. Assumptions 2 and 3. Second one is that the variance is constant over time. So we don't have like a triangular pattern in our data where the variance is very small at one time point and explodes at later time points. Assumption is that constant variance over time. And the third one is that the auto-regression or auto-correlation between the outcome is the same as for any equally spaced observations. So if I have something like time 1 and time 10, the autocorrelation between those two things, which are 9 time points apart, would be the same as time point 11 and time point 20. That the model assumes that the carryover autocorrelation is constant for any equal spaced width, any interval of equal spacing rather, regardless of where that equal space occurs. So if it's the first, 9 time points apart at the beginning, 9 time points apart at the end, the autocorrelation should be similar. The autocorrelation only changes as a function of interval length. So time 1 and 2 can be more correlated than time 1 and 10, but the correlation between times 1 and 2 should be the same as between times 49 and 50. Okay. So those are the assumptions there. Yes. And this gets related to that last assumption, just says that autocorrelation effect is assumed to apply to all time points. So I'm not estimating a unique carryover effect between time 1 and time 2 and time 3. I'm assuming that 0.35 that we saw in the output, that corresponds throughout the entire series.